How do we interpret ECoG signals with high variability? Imagine trying to understand a conversation where the words keep changing and the tone shifts unpredictably. That's similar to what scientists face when interpreting electrocorticography signals from the brain. Electrocorticography signals are electrical signals recorded directly from the brain's surface, capturing the combined activity of thousands of neurons. These signals are naturally very variable because the brain is always active in different ways, depending on what you're doing or thinking. Plus, different parts of the brain produce different patterns, and ongoing mental or physical tasks can cause fluctuations. So, how do researchers make sense of these constantly changing signals? The first step is focusing on specific frequency bands, especially the high gamma range, which is around 70 to 110 Hz. This frequency range is closely linked to local brain activity related to tasks or movements. By filtering the signals to isolate these frequencies, scientists can better spot meaningful patterns and ignore background noise. They use techniques like spectral analysis and time-frequency decomposition to see how these oscillations change over time, helping to identify relevant neural activity despite the variability. Next, advanced statistical and computational models come into play. Methods like statistical parametric mapping compare current signals to normal baseline activity, helping to highlight deviations that could indicate important brain functions or abnormalities. Machine learning algorithms are also used to decode complex multi-channel data. These models learn to classify different states, such as whether a person is about to move or think about something, turning unpredictable signals into understandable information. Another key approach is looking at the spatial and temporal context of the signals. Because ECoG has high spatial resolution, it allows scientists to map activity to specific brain areas. By comparing signals across different electrodes and over time, they can find patterns that relate to particular actions or thoughts, even when the signals fluctuate. This mapping is especially useful during brain surgeries or when developing brain-computer interfaces. Correlating signals with specific tasks or behaviors also helps clarify their meaning. For example, during movement tasks, certain rhythms in the brain increase or decrease in predictable ways. By linking these changes to specific actions, researchers can distinguish relevant signals from background noise. Pre-processing the signals to remove artifacts is another important step. Muscle movements, electrical interference, or electrode shifts can cause false fluctuations. Carefully cleaning the data ensures that interpretations are based on genuine brain activity. In real-time applications like brain-computer interfaces, dynamic analysis tools provide immediate feedback. These systems adapt to ongoing changes, helping to interpret signals accurately even when the brain's activity varies during different tasks or states. Practically, these methods enable decoding motor commands or speech intentions from ECoG signals, allowing control of external devices. During surgeries, they help map critical areas for language or movement, even with individual differences. In epilepsy monitoring, analyzing statistical deviations and phase amplitude coupling patterns helps identify epileptic zones. In short, interpreting high variability in ECoG signals involves combining filtering, statistical modeling, spatial temporal analysis, and task-based correlations. These techniques turn complex, fluctuating brain signals into meaningful information that advances neurotechnology and clinical applications.